My name is James Woolcock. I'm the Engineering Director at Bastian, and today we're going to talk about metal 3D printing. So the metal 3D printing that we do is with titanium, and we run two Renishaw machines that use a laser to melt titanium powder layer by layer to build up parts in an additive fashion. So we're printing basically what we call the lugs of the bicycle, or the nodes. So the bottom bracket, head bracket, upper and lower, seat bracket, and the dropouts, as well as a seat topper. And then we bond those lugs together with carbon fibre tubes for our bicycle frames, but we're also making a variety of other components and parts in titanium. For us, one of the main advantages of this method of building a frame, the 3D printed titanium, is the ability to customise the frame easily. The lugs, the nodes of the frame are the things that allow us to do custom geometry and custom stiffnesses and that kind of thing. But also the ride characteristics. We get the benefit of the bulk stiffness of the carbon fibre tube for torsional rigidity of the frame. But then we have the titanium at the nodes, which gives us some of the high frequency vibration damping. So the road feel of our frames is also super smooth. So certainly it's not a mass production technology. It's better to think about it as a mass customization technology, where you're not trying to make thousands of things per day. It's being able to do something subtly different each time. So the end-to-end process for us starts with design. Obviously we have to have the CAD data and the CAD design ready. We do bespoke individual CAD for each bike, and then that data gets exported. We add a structural lattice to the interior volume of that, and then pass to another program which slices that data into machine code for the printer to use. So our machines have a build envelope of 250 millimeters square and as high as perhaps 330 or 340 high. Obviously you need to have quite a lot of powder on hand to print that high, but we have one of our machines has that extended Z height, and we Tetris parts into that envelope and fill it as much as we can each build. Once we hit play, essentially, on the printer, usually we run for about 2 days. Sometimes a little bit longer. If it's a particularly high build, it's going to run for long, but we're pretty much on a 2-day cycle on each of our machines.
So these printers essentially run off a really strong laser. The laser essentially in very minute points is welding or melting the titanium powder, and in the end creates a 3D piece for us. The laser point is at about 1700 degrees Celsius, so it's really, really hot, and the way we're able to achieve it being that hot is having it in a chamber that is zero oxygen. So there's no oxygen in there. It's filled with argon because the titanium powder is quite reactive to oxygen. So if there was oxygen in there, it would just be a fire pit, so it wouldn't work at all. So very important to make sure that the chamber is got no oxygen in it, essentially.
After 2 days of the machine running and printing parts, you're left with a build plate which needs to be recovered, and all of the powder which wasn't consumed gets recovered and recycled. So we bring the build plate up, the dry powder essentially gets sieved and put back into the machine, and then that build plate needs to go into heat treat. So there's still residual stress inside the parts from their printing process. So that whole build plate goes into a furnace, which is also under argon, and goes through a heat treat annealing process. We do test samples on every build as well to make sure that we're getting the yield stress we expect.
So these little pieces here are tensile test sticks. We use them to test the material properties of the titanium. Sometimes things happen with the printers and not every plate comes out the same, and so it's a good sanity check for us to make sure that the titanium printed is at the standard that we want it to be at industry standard, and then so that things don't break underneath us.
From that point, parts that are on the build plate can be cut off. Supports, the sacrificial supports needed to print the parts are removed, and then they move into machining. Definitely parts that come out of the printer are not 100% ready to be used, especially if they've got a bearing interface or a precision fit portion, threads that need chasing. We do print in threads, but we need to chase them to clean it up. So there's quite a few machining operations depending on what the end use of that part is. And then from machining, we have quite detailed surface finishing. So this is sacrificial lattice that helped the part build off the plate. So it was printed in this orientation. Obviously all that lattice work gets knocked off, and then through our surface finishing process we get closer to a finish like that. This one's still got a little bit of polishing to go, it's not quite there, but it's almost a finished part. Once we have shiny titanium, in parallel the carbon fibre tubes have been prepared for that bike. So once the build went down to print, another drawing went for carbon tube preparation. So the tubes have been cut to length specific for that frame, and then the titanium and the carbon will come back together behind me here in composites, and we have quite an elaborate bonding process to work through so that the parts are completely clean and both sides of the bonded joint, when they're both ready, they come together and get bonded into a frame behind me here in composites. We have been using the 3D printed titanium and producing these bicycles since 2015. So in terms of the technology which actually melts the titanium, that hasn't changed for us for the last 5 years. Certainly the cost of the machines is still quite high. There's still barriers to entry. It's more, we are running 2 single laser machines. The latest machines that are coming out now have quad lasers and perhaps able to print faster, but fundamentally it's still the same technology. I think it's unlikely to see whole rear ends or whole frames being printed economically. Like it's not at the point for speed or cost where that's going to be a path forward, I don't think. The next frontier is certainly the automation of a lot of the ancillary functions around the machine. So the machines that we run are manually sieved, so we're still manually handling powder, and the heat treat process, it's a separate unit for us. So yeah, there's definitely machines coming onto the market now that are more end-to-end, that do all their own internal powder handling and heat treat process, and then can reload a build plate for themselves and keep going. But it's not going to be as fast as stamping parts. It's not going to be as fast as hydroforming parts. It still needs to have, you still need to have a strong reason to choose printing, whether it's customization or ultra lightweight, high stiffness ratio. You can't make thousands of parts per day with this type of technology. Certainly we're highly invested in the metal 3D printing and can see it's got a lot of potential into the future. So we're excited about where it's going to go.